In this video, I'll be continuing our discussion on Euler's method to solve first-order differential equation. Particularly, we're going to look at the rest of example 5.1 on page 101. Okay, so in the last video, we talked about how we can solve differential equation like this, shown in equation 5.6 using forward Euler. And today I'm going to show you how we can do the error analysis and really understand what is the order of approximation using Newton's method. Using Euler's method. Okay, so let me just jump directly to the spreadsheet we did before. This is the spreadsheet we used before to solve the differential equation. And I think equation 5.6 of the textbook. And if you recall, I did three different delta H or delta T or delta X, whatever you call it. And we had three tables. So now I'm going to plot the error. So this is the error, the difference between the approximation and the exact. I'm going to plot the error against time. I'm going to plot the error against the delta H. So basically against time and delta H. So this is the plot. On the y-axis, I have the percentage error against time, but the colors are showing different delta T. So from blue to red to green, delta T is going down by a factor of 10, right? So we did Euler's method with delta T of 0.01 and then 0.001 and then 10 to the minus 4. So if you look at the difference between the blue and red almost anywhere is about a factor of 10, right? The difference between this and that is almost a factor of 10. That means if you get the blue curve, you divide it by 10, most likely you get the red. And if you get the red curve divided by 10, you get the blue, you get the green, right? And that's exactly how the error goes down as you lower delta H. Because this is linear with delta T, we call it a Euler's method, or forward Euler's method is of order 1, or it's first order approximation to the derivative. Okay, so that was all about example 5.1 of the textbook. I'm going to close this and jump to the next topic, which is now backward Euler. So we're going to we're going to skip for now the stability analysis. We're going to come back to it later. So we're going to focus on the backward Euler, and if time permits, I'm going to also talk about the trapezoidal rule to solve differential equations. So you see very close connections between the ways we solve differential equations and the ways we do the derivative numerically. We had, if you remember, or maybe the integration numerically. So in the numerical integration, we had trapezoidal rule. In the same way, we have here the trapezoidal rule for solving differential equations. We also had forward and backward difference for for numerical derivatives. We do have the same almost way to solve the differential equations using backward and forward Euler, or backward and forward difference. So we saw forward difference or forward Euler before. Right now we're going to look at backward difference or backward Euler. Okay. So we pretty much follow our technique. That means we only discretize the derivative. We have dy dt, which is discretized to now yn plus 1 minus yn. So you would think that this is pretty much like forward Euler because you're subtracting the point ahead of yn and you divide the thing by delta t or delta a or delta x or h, right? However, the right side is a bit different. So in forward Euler, we had f of yn tn. This time we have yn of plus 1 tn plus 1. Let's look back. In forward Euler, we had yn plus 1 minus yn divided by h, and then that equals to f at point yn. But now we have f at point yn plus 1. And that is the difference between forward and backward Euler. Okay, So the best way to see that this is actually really backward, you can replace n by n minus 1. So if you do that, if you replace n by n minus 1, excuse me, then you get something like this. So let me just move this over here and make it red. Okay, so then you would get yn minus y, and it's a bit tricky, let's say n minus 1. So I'm writing the subindex as underscore. Okay, so this, I'm just replacing n by n minus 1 in this equation. Okay, so divide by h, that's equal to f of y sub n and t sub n. Okay, now look back. So now on the right side I have y and tn, exactly like in forward Euler, right? In forward Euler we had y and tn as well. This is y and tn. Now on the right side are the same, but the difference is the left side. The left side now becomes yn minus 1. Now this thing is very familiar to you. This is backward Euler. If you're sitting at point n, you're looking the point on the back side, right? But these are almost, they're exactly identically the same. Okay. The only thing we did was just replace n by minus 1, so we didn't change anything. Well, I just wanted to show you that this is also the backward Euler. Don't think that this is forward Euler. Okay, so how we can go about doing this? Well, let's specifically look at one example here. Let's say we want to do the same example now using backward difference. In backward difference, we discretize or rewrite the left side as yn plus 1 minus yn divided by h, and on the right side everything has to be at yn plus 1, exactly like equation 510. Okay, and by doing so we can solve for yn plus 1, assuming that yn is known, because yn is always the current point, and we assume that the current point is known. The question is how we can calculate the next point, which is yn plus 1, and then here we solve for yn plus 1, which turns out to be this expression. So this is very suited for spreadsheet calculation, because if you have yn, then you can calculate yn plus 1, and then the rest of it would be dragged down. Okay, so let's look at the result for example 5.2. Okay, so this is 5.2. I'm going to increase the font a little bit. All right, so this is, we have t from 0 to 0.1, the separation of 0.1. Y exact is as before. We know the exact solution. The problem or the exact solution is given to us. This is just for comparison, not really to calculate anything. And error would be the difference between the exact and the approximation divided by exact. You get the absolute value, multiply by 100. There's no big deal here. The only thing here is how we can calculate the y. All right, so the first y is known. That's the initial condition is 5 as before. And if we don't remember that, pretty much like in forward Euler, basically the y at t0 is 5. So we are not solving anything yet. We're just substituting the boundary condition. Okay. The only part of solving this problem is this cell. This cell is the only part you have to do. The rest is just right down. Okay, so let's look at this. This is equal to the previous y value, which is the blue cell. And right here. Okay. And let's look at the exact way we did it. So in backward Euler, we solved it this way, right? We solve for yn plus 1, which is going to be the previous y value plus 7 times h exponential of minus 0.5 times the next t value, right? This is tn plus 1, and then 1 plus 2 times h. Okay, so let's look at that. And that's equal to the current the previous y value plus 7 times dt, which is the green cell, okay, then exponential of minus 5 times the next t value. So if you're sitting here, right, So hopefully you don't get confused about n and n plus 1. So when you're sitting here, when you're calculating the y value for this cell is corresponding to n plus 1, right? Because you're doing the right side, no, you're doing the left side. The left side is n plus 1. And if that is n plus 1, then you can figure out what t n plus 1 is, right? If this is y n plus 1, this thing should be tn plus 1. So this thing goes into the exponential, minus 0.5 tn plus 1, right? So hopefully you don't get confused. Don't put here mistakenly this cell. It has to be the purple cell. Okay, divide by 1 plus 20 times h, which is the green cell. That's what it is. And that's the only part of the solution. Then we need to take care of. The rest is just drag down. So I'm going to hit enter. And all you do is you drag this guy down. Exact solution, you need to hard code this. You just drag this guy down too. And error analysis, if you do the error analysis for the first element, which is the difference between approximation and exact divided by exact, the rest is just drag down. There you go. You can also go ahead and plot. Let me see what I plotted here. Yes, so you can plot y against t. So to see how good the solution is. So far we did only for one dt. We can repeat the same thing for another dt, which is smaller than this one by factor of 10. So we divide the h by factor of 10. We redo the same thing. We plot it, and I think almost. Let's see. Yeah, so these two are almost identical from this resolution. You can see that almost overlapping. Now, if you also lower delta t by another factor of 10, then you get another table. So for this table, you have to have actually 1,000 rows. So hopefully you know how to do that by just double-clicking on the right corner whenever you want to drag down. So all you do, again, you write the equation for this cell, you then double-click on this lower right corner, and it's going to populate the equation all the way throughout, as long as you have the first column populated. Okay, so it's going to stop at the end cell. So I'm not going to show you, it's about 1,000 lines below this. All right, so then we're going to go ahead and plot the error as a function of time on this same chart right here. So now we have, well, these are the curves. These are the y against t, right? And the green one is, let's see, the green one, I'm going to click on the green one. Okay, so yeah, it looks like green one is the largest dt, right? And then for the other two dt values that we calculated, we have this purple one and the blue one, which is right overlapping the purple one. The exact one is also red. We have the exact solution, right? The exact solution is this third column. We can also overlay on top of the other one. And we see that basically the red is pretty much like the purple and the blue, which means these two dt values are really close to the exact one, or at least gives us the solution which is really close to the exact solution. But the best way to compare them is just to look at the error as a function of t. And you see that, again, our t, so this is the error for dt equal 0.01, this is 0.001, and this is the error for 0.0001. And you see that every time we divide delta t by a factor of 10, the error goes down also by a factor of 10, right? So this red line is 10 times smaller than the blue, and then the green is 10 times smaller than the red. By the way, this is logarithmic scale, so you can easily see that it goes down by a factor of 10. All right, so what is the point here? The point is that backward Euler is also first order. You divide delta t by h, the error goes down by a factor of h. So that means the error is proportional to h. And because the power of h is 1, we call backward Euler is also first order. So the upshot is all Euler's method, forward or backward, is first order approximate. Okay, so it's first order approximation to the derivative. In the next video, we're going to look at trapezoidal rule and also do the same error analysis to see if that one is also first order or second order. Alright, so thanks a lot for watching. Stay tuned for the next video on solving differential equations numerically using trapezoidal rule.